to prove that for any integer n, that n cubed minus n is even. And this is a great example of proving this by cases. And our first case is going to be when n is even. So case 1, we're going to say n, which is in an integer, is even. So by definition, that means n is equal to 2 times k, where k is some integer, right? It's a multiple of 2. All right, and then we want to see if we can write n cubed minus n as a multiple of 2. Well, if n is equal to 2k, then this is 2k cubed minus 2k, or 8k cubed minus 2k. Now, if I factor out a 2, I leave behind 4k cubed minus k. And since the sum, product, and difference of integers is an integer, this is equal to some integer. We could say L, in which case n cubed minus n is even. Perfect. So what we were able to do, just to recap, is if n was even, we could write it as 2 times k. We plug it into n cubed minus n, and we show that that expression is equal to 2 times some integer, which by definition means it is even. All right, let's look at case 2. Case 2, n is odd. And so by definition, n is equal to 2 times an integer plus 1. All right, and we want to explore what n cubed minus n is in the case where n is odd. So that would be 2k plus 1 cubed minus 2k plus 1. Now, if we expand this either by multiplying it out in steps or the binomial theorem, we get 8k cubed plus 12k squared plus 6k plus 1. You can verify that. Minus 2k minus 1. Now we see here the 1's go away, and I have all things that are multiples of 2, so I can factor out a 2 here. We get 4k cubed plus 6k squared plus 3k minus k. And since the sum, product, and difference of integers is an integer, that there is an integer as well. So we have been able to show that n cubed minus n is even in all cases. So that's the end of our proof.